this lesson is square root functions. Sometimes they're called radical functions. So just know that these are the same thing, radical function. So it just means that you're going to see a square root sign, or you could call it a radical. Okay, so we are going to model and solve problems using radical functions. Alright, so main idea. A radical function is a function whose rule is a radical, this should say expression, not expressions, sorry. Okay, so here's what it normally looks like, just that. So go ahead and use Desmos or use a graphing calculator and sketch your little graph, and then we'll talk about the domain and the range. Alright, so these graphs always look like, kind of like a hill. They're slightly sloping. So if you'll notice, the graph definitely starts at 0, 0, and then it continues going right forever. So when we talk about domain, remember domain is our x values, so we would say domain is anything greater than or equal to 0. And if you look at your table, you have an x value at 0, 1, 2, 3, 4, 5, 6, but you don't have anything in the negative, so you get an error message. And that's because of that idea that imaginary numbers are used when you take a square root of a negative. Okay, our range is actually going to be, if you'll notice, the lowest y-coordinate you ever go to is 0, and then it kind of steeps up forever. So we would say the range is anything greater than or equal to 0. So that's our y value. So that's a little review about domain and range. Domain are your x values, that could be possible, and range are your y values. Alright, so we're going to look at some transformations. So kind of similar to that first unit we did on transformations, but these are a little bit different. We're talking about just taking a function and moving it a certain way. And what I'm going to show you is some weird notation that you can see, especially in higher level math courses like pre-cal. And then we'll look at some examples. It's usually not that bad. Okay, so this is what we would call the parent function. Anytime I say the word parent function, I mean the original before a transformation happened. It's kind of like in that first unit when we talked about the preimage, your parent function is your preimage. Alright, so we're going to look at a vertical translation. Remember, vertical means up or down. And this is the notation for it. So you would take f of x and you would just add a number k to it. So remember, f of x was x. It's saying if you add a number outside of that radical, it's going to move it either up or down. Okay, so we know that the parent function looks like a heel, and then it starts at 0, 0. So what I want you to do is sketch an example of these two functions down here, and then we'll talk about what that 3 does to it and what that 4 does to it. So go ahead and pause the video and sketch it in 1, 2, 3. Alright, so when you added this 3 outside, it moved the graph up 3 units. And if you have a hard time telling, so right here, we started at 0, 0, and this graph starts at 0, 3. That's how we know it moved up 3 units. This minus 4, it moved the graph down 3 units. Oh, sorry, down 4 units, sorry. Alright, so if you add a number outside the radical, it's going to move it up. If you subtract a number outside the radical, it's going to move it down. That's your vertical translation. Alright, so now let's look at the horizontal translation. So a horizontal translation is actually going to do some stuff inside. So it's talking about if I add or subtract a number to x inside the radical, it's going to move it either left or right. And it's actually going to move kind of opposite of what you think it would. Okay, so we know the parent function starts at 0, 0, looks like a heel. I want you to graph the two examples. Notice that it's x minus 2, all of that inside the radical, x plus 1, all of it inside the radical. Go ahead and sketch a graph, and then we'll talk about what happens. Alright, so here's what happened. When we did minus 2 inside, it moved 2 units to the right. And it's kind of opposite of what you would think, because you would think if it was a minus, it would move it to the left. But when you do stuff inside, it actually moves kind of backwards. The +1 inside moved 1 unit to the left. Alright, and once again, if you're having trouble finding it, look at where the vertex is, and you can see that it moved from 0, 0 to 2, 0, from 0, 0 to negative 1, 0. Okay, so now let's look at a vertical stretch or compression. So this is a number in front of the radical. Alright, so I want you to graph the two examples, and we'll talk about what happens when you have a number in front of the radical. How does it change the graph? Alright, so here's what happened. This 6 made it stretch, so notice it looks like you took the graph and you pulled it up. And then the 1/2 in front of the radical made it compress, so it looks like you smushed the graph down. Alright, let's do the same thing with this one. So this is going to be a horizontal stretch and compression. This is when I'm going to do like a number in front of the x, but inside the radical, what happens. So go ahead and graph these, and we'll talk about what happened. Okay, so the 1/5 in front of the x is a horizontal stretch. Think about if you were I don't know, stretching the graph to the right. And then the next one is the horizontal compression. Think about smushing that graph, but smushing it horizontally. Alright. And then you can have a reflection. So we're going to look at what happens when you have a negative in front of the radical and what happens when you put a negative inside the radical. So go ahead and graph these and we'll talk about them. Alright, so for the first one, when you have a negative outside the radical, you're going to reflect or flip over the x-axis. And whenever you have a negative inside, it's going to flip over the y-axis. So that's the difference in those two. Okay, so if you're ever asked a question about transformations and you don't know the rules just by looking at them, then graph it and just tell me what happened. It's really simple. Okay, so now we're going to actually model and solve problems with these radicals. So I converted this file from Word, and then I'm using my Apple iPad to do this, which is why my equations don't come in. So that's why I wrote them at the top, or haven't written them. Sorry about my grammar. All right. So you can read this really quickly to yourselves. Okay. So S is referring to speed, and it tells us that the car is 90. So I'm going to replace S with 90. And X is the length of the tire marks. So what I need to do is figure out what X has to be in order to get 90, or I can work backwards. So 2 is being multiplied to the radical. To get rid of multiplication, you divide. So 45 equals the square root of 5x. Anytime you want to get rid of a square root, you would square both sides. Remember that that radical and that square cancel each other out. So you just need to figure out what 45 squared is. Alright, and then the last thing I'm going to do is divide by 5 on both sides. So the length of the tire mark would be 405 feet. Alright, take a minute and read this problem. Alright, so for number 1, S represents how fast you're going, your speed. That's what I'm trying to find. D is the length of your tire mark, so I know that my skid mark, I hate using the word skid mark because it sounds like something else, is 115, so I'm just going to put this in my calculator, and I get approximately 49.14. Okay, I'm going to do the same thing with the next one. Okay, so this time I know the speed is, I'm going to write it down here, sorry, 60. I don't know the length of the tire mark, that's what I'm trying to find. So the first thing I need to do is get rid of that square root. I do that by squaring both sides. Remember that when you square a radical, it cancels out. So this is 3600 equals 21 times D. Last thing I'm going to do is divide by 21 on both sides. So D is, I'm rounding a little bit, approximately 171.4. Alright. And then the last question, does doubling the length of the skid double the speed of the driver? So I'm going to double that number I just got. So about 342.9. is now going to be my new distance. And I'm just going to plug it in. And I'm going to see if doubling it actually doubles the speed. So I get the speed is 84.8, which is not double 60, so I would say no. Okay, so I want you to see if you can figure out what goes what and what we're trying to find. Okay, so this one is kind of tricky. So it says that it is compressed vertically by a factor of 3/5. Anytime I want to compress or stretch vertically, that's when I put the number in front of the radical. That's why I have 3/5 in front of that radical. And then x is talking about you're bouncing x feet in height, and it's talking about a 45-foot bounce. So I'm going to replace x with 45, and all I have to do is put this in my calculator. So approximately 32.2. Okay. So I think this one is a more difficult question. I don't really like it, just to be honest. Alright. Go ahead and read this one, see if you can figure out where things go and what you're trying to find. Okay, so this one's also hard because it says horizontal compression of 3/5. That is when you put the number in front of the x inside the radical. That's why I have 3/5 inside the radical. X is representing radius, and I know that the can is 2/16. So what I'm trying to do is work backwards to figure out what x equals. So first thing I'm going to do is I'm going to square both sides to get rid of that radical. I'm going to divide both sides by 3/5. Make sure you're putting 3/5 in parentheses. And then to get rid of dividing by 40, I'm going to multiply by 40. So this one's a big number. Alright, and I think that's what you should get. Alright, let's do a couple more. Alright, so go ahead and read this problem. See if you can figure out what S of D and what D represent and what you're trying to find. Okay, so we're trying to figure out the speed when the depth is 1500. So D stands for depth. If I know it's 1500, I can just replace it. So all I have to do is type this in my calculator. Might help if I type the right number, sorry. Alright, so I got 149.5. Alright. Alright, this one looks really big, bad, and scary. It's not supposed to be. I say, go ahead and read it and see if you can figure out where to put things and what you're trying to find. Okay. So this is a science formula. It's called the Jeans mass formula. And we're just trying to figure out, will the clump form a star? So we're trying to figure out, if we plug all this in, will it actually equal 137? It sounds more complicated than it is, but you just need to make sure that you're putting things in the right places, using parentheses when they use parentheses, all that kind of stuff. Alright, we're just trying to see, is this equal? So I'm going to put the right side in my calculator. And when I do that, I get that this side is 100. 100 does not equal 137, so my answer would be no. It will not form a star. Okay, so try this one. Read the problem, see if you can figure out where to plug stuff in, and then we'll talk about it. Okay. So I think this one's tricky because you're actually talking about two different formulas. Not two different formulas, but two different scenarios, I guess. So one you're talking about Earth and one you're talking about the moon. Okay, so G is standing for gravity. You have 32 when you're on Earth, but the moon's gravity is a 6 of that. So if you'll notice in this one, I times 32 by 1/6, and that's because it says the gravity was 1/6 of that. The radius is pretty much the same on both, so now I'm just going to type these two in, and I'll figure out how much faster it is. Alright, so those are the differences between the Earth and the moon. Alright, once again, I think that's a pretty hard problem. I don't really think you'll have these harder problems, but I wanted you to be prepared in case you ever do encounter them. Alright, go ahead and read this one, see if you can figure it out. Okay, so for this one, D is standing for distance, and D of A is talking about altitude. So it tells me the altitude is 11,000, and now I'm just going to work backwards to figure out the distance. So first thing I'm going to do is get rid of that 3.56 by dividing by 3.56 on both sides. And I get 3,089. I'm going to round this to 888. And then the last thing I'm going to do, the way you get rid of a square root is you square both sides. And this is a really big number. So approximately this much. Alright. So here's a little pumpkin because I got bored. Let me know if you have questions. Try your assignment. And I'll talk to you later. Okay, bye.